Hey, this is Mr. Weiss. If you're seeing this, you might be watching this because you missed the video. So this is May 7th, and this is 10th grade physics for 10C. And yeah, today we're going to be talking about hearing problems and solutions. I'm going to wait till folks start coming online, and as they join up, I'll give them some participation points. So as soon as you're there, hello, and wish me hello so I can grant you some points for participating today. So let me know who's there. Kira's there. Super. Glad to have you here. Sure. Okay, who else is joining up? There's another person or two, so let me know, and off we go. Pia's here as well. Isabel's here. Henry's here. Welcome, Henry. Christina's here. Super. Very good, Christina. While we're waiting up for people, I'll just tell you we're going to review hearing for a few minutes, how our hearing works, the physics of it. Then we're going to talk about some hearing problems and solutions. And if we get that far, we'll talk about ultrasonic and infrasonic and sound and what we can hear and what other creatures can hear, and maybe why that's important. Okay, got another person or two joining me, so go ahead and let me know you're there once you get seated. Chelsea's here too. Good. Carla's here. I have a boss here. You'll have to tell me who you are. Teo. Okay, good, Teo. Glad you could join us. And Kellen is here too. Lucas is here. Super. Okay, 1, 2, 10. Got a couple more, still need to say hello. So go ahead and punch in and I can give you some points for participating, and then we'll get started for the day. I'll take about one more minute and then we'll start reviewing, especially for folks that weren't here last time. I got a couple things to show you today. Felix is here. And I've got Maya and Natasha are both here. Good. Okay, so I think we'll go ahead and start up. When others join, I will simply add them in. Okay, so we got something to show you here to start the day off. Voila! Like Dumbo, huh? Isn't that great? So it's a big flipping ear, and we're going to remind ourselves of some parts. Okay, you can answer some questions for me from last time. So here we got the outer ear, and we know why that's big. We got the ear canal, and then We got this puppy. Hold on, not that. We got this, right? Okay, so questions. First off, what is this called? And second, what's the physics? What does this do as a term that you and I learned? Okay, so what is this thing? It's at the end of the ear canal. And give me the physics that it does that we studied. Okay, several of you got the name of it. It's an eardrum, that's right. And then how does it work? What's the physics behind it? Great, a lot of people got the name. And the rest of you who haven't signed in, let me know. Say hello so I can write your name down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got about 3 of you need to say hi. Amalia is here. Hi, Amalia. The sound causes a forced vibration. Thank you, Chelsea. That's exactly right. So whatever sound it is, if it's a low sound, right, maybe 100 hertz, then that hits it and it has to vibrate at 100 hertz, okay? If it's a high sound at 400 hertz, it has to vibrate at 400 hertz. So it doesn't have a choice. It's forced to vibrate at whatever sound hits it, okay? Huge. And yes, a lot of you are saying that as well. Good. Then we got these guys. They kind of fell off the model there, and away they go. They're 3 really small bones. And of course, we talked about the last time, they carry the vibration to this guy. And I'm going to lift this up. And the main part of this for sound is this part that looks like a snail. In German, it's called Schnecke. So my question to you is, first off, what's this snaily part called in English? And second part will be, what's the physics involved that allows you to hear once the sound wave gets into the snaily part? So the snaily part is called what, and what's the physics that goes on in the snaily part? Yes, good. Okay, several of you got the name. So it is like Felix and Kira got it. It's the cochlea, right? Several others got that too. And what's the physics of this? How does, when the wave gets in here, what's inside that allows us to hear? If you weren't here last week, you want to see that video. The sound is amplified. It is amplified mainly in the bones, Chelsea, and in the ear canal, but not in the cochlea. The sound is captured there, but how is it captured? They act as a lever. Now, the bones that I just dropped, the 3 bones act like a lever, but the inside the cochlea, something else is happening. Here we go. Yes. Okay, good. It resonates. Good. What's it? Maya says it's filled with fluid and different length cilia. Good. The cilia are little hairs inside this hair-like features. Good. And they have different lengths. Good. Some of them resonate. So not just it, but let's be more exact. So some of them resonate. When they resonate, what does that do? Remember, this is connected to our brain, right? Each of these on each side of your ears, connected to your brain. When the cilia resonate, so what? So continue statement. When the cilia, when some of them resonate, they tell the brain what? Waiting for a couple responses. Anybody else out there, let me know you're here if you haven't already. Well, I'll just read. I don't have Leah. I don't have Mike or Christian. I don't have Luca, Amelie. I don't have Lucas Moscow. I don't have Lena. I don't have Tilly. I don't have Helen Stahl. Good, I'm getting some answers here. Good. They inform the brain of the relative frequency. Exactly, Amalia. Right. And Chelsea adds, the sound matches the natural heat frequency of the cilia, of some of the cilia, causing them to resonate and inform the brain, oh, I'm this cilia, so it's a 440 hertz. Hey. Exactly. Good. Through the auditory nerve, adds Maya. That's correct. Good. All right. Remember, I'm keeping an ear out for you. Okay, never mind. All right, so there's our ear. Whew, it's kind of a heavy ear. Have I talked your ear off yet? Just about, huh? Okay, so what are we up to today? Hearing problems and solutions. let's first talk about, well, first let's ask if you got any questions. So, anything so far from you? Christian's saying he's here. Thank you, Christian. Yeah, looks like a lot of you have that idea. Good. Anyone else here? Let me know. Okay, then let's talk about what you and I hear. Okay, we hear certain frequencies. What are they? So humans hear. The assignment I'm going to give you on bats says it a little differently, but I've always heard about 20 hertz. 20 hertz would be like this, low, 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 low. I'm not a bass. I can't sing that low. I need somebody to sing really low bass. Very good. I hear somebody. Okay. All right, good. And then we hear about up to 20,000 hertz. That would be a really, really high sound, as high as you can imagine, and still hear. All of you hear better than I do. Okay. As humans get older, we tend to lose some hearing, some more than others. Okay. And interestingly enough, men tend to lose the high frequencies first. By the way, guys, hate to say it, but men tend to lose their hearing more than women. Some women do too, but an awful lot of men. And ironically, men seem to lose the high frequencies first, which happens to be the hearing of their wife's voice, the frequency of their wife's voice. A kind of sick humor from nature, right? So, hearing loss is often the higher frequencies. Even I don't hear what I used to. Sometimes I hear a young person go, "Oh, I hear, oh, that's so loud," and I don't hear a thing because it's super high. So generally, I've lost some of my upper range. Some of you are going to hear things that I don't hear anymore. Well, okay, you've probably got parents or maybe grandparents that have hearing loss. What do they do? How do they solve the problem? Do they get a bigger ear like the one I showed you? No. Okay. So yeah, they wear hearing aids. Okay, so let's talk about a hearing aid. So what do? They're very adjustable, right? You need to get one and get it really fitted for your hearing loss. Okay, so for example, if I've lost maybe above 18,000 hertz, then I've got to have that portion amplified. So they've got to take it and adjust it for me. If later on I lose more, then they have to have it adjusted. Maybe I lose a lower frequency, they have to have that adjusted. So they amplify specific frequencies lost. You might have had a traffic accident or something. There's also other ways to lose your hearing. Some people are born with hearing deficiencies, and either through surgery or through hearing aids, they've got to have a way to hear as well. Okay. If you have any special hearing questions, let me know. I don't know the answer to everything, but I know some things, so we can talk about them. Okay. I want to talk to you for a sec about old men and chainsaws. I come from Montana, and it's a place where a lot of guys get out there with chainsaws and cut their own wood, and then they burn the wood for heating. But some of them, for many years, did not wear ear protection, and so their hearing is really shot. They can't hear much. They've lost lots and lots, not just the higher end, but a lot of that frequencies, okay? What happens is the cilia, right? The cilia, when they're overstimulated, at a certain point, they can get stiff, and then they don't respond as well. So you can make them respond if you amplify the frequency more, but at a certain point, you may lose your hearing so much that they simply won't move. They get stiff and they freeze up. Tilly's here. Thank you, Tilly. So your hearing can freeze up. Now I'm going to sound like your mother. Have you ever gone to a club and you come out and your ears are kind of ringing? Well, don't do that all that often, because it turns out you do damage your ears even as a young person. And so if you spend a lot of time in clubs, your hearing loss occurs in your 20s instead of your 70s or 80s. So, yeah, okay. By the way, of course, your hearing does come back after you've been in the club, but if you keep doing it, it doesn't come back, and the little cilia do stiffen up and don't work as well. It's just part of the physics of the whole thing. Ute, before I forget, let's talk about some other creatures. Okay, make sure you can still see what I'm writing. If I've got, we're going to come back to hearing in a minute. I got something else to show you. But for now, if I can hear greater than 20,000 hertz, I take that back. Let's talk about different types of sound first. So let's say there's sound. This was sound that is the range of hearing, right? That's audible sound, right? This is audible, means humans can hear it. If I have over 20,000, it's inaudible. What's it called if it's greater than 20,000 hertz? What do you think? Or if it's less than 20 hertz? Tell me if you know either word. Luca's here. Thank you, Luca, for checking in. Let me know what either word means and tell me which one you're talking about. Inaudible. Yes, Amanda, you're right, but I need something a little more exact. You're right. I can't hear either one of these. They're inaudible. But there's another one. Okay. Christian says ultrasound. Yeah, which one is that? And then I need the word for lower than 20 hertz. And I need to know. Okay, ultrasound, he says, is higher frequency. Thanks, Christian. You're exactly right. So higher than 20,000, this is ultrasonic. Ultrasonic sound. And I got another one from Isabel, and she's right. Good go. She says infrasonic. Infrasonic. Well done. Good job, folks. It works the same way with light, okay? You've heard of ultraviolet light. That's higher frequency than violet. We can't see it. You've heard of infrared light. That's lower frequency than red. So that's beyond the visible spectrum. Ultraviolet, higher than what we can see. Infrared, lower than frequencies that we can see with our eyes. Different kind of wave, I know, but similar idea, right? Okay. Let's change boards. I told you about a second board, right? Yeah, you know that already. So you're not going to be impressed today. Who hears, and I'm talking about who meaning what creatures, who hears ultrasonic? And there's more than one answer. Who hears infrasonic? So, give me a guess and tell me who your guess is for. Here's Okay, so make a little sentence for me. Who hears what? So don't just give me a creature. Tell me which one you want it for. Otherwise, I can't write it up there. I don't know what you're talking about. Yeah, I'm getting lots of creatures. So what? Tell me which one. I got ultrasonic or infrasonic. So where you want your creature? Christian says Wales. That would be the country, but I think you're meaning the creature. Wales hear infrasonic. He's right. Really low sounds. You and I can't hear them. Whales. I got stories to tell you about whales. Very cool, but I'll come back. Elephants, Isabel, you're right. They also hear infrasonic through several kilometers through the ground. You guys are pretty good. I need some ultrasonic sounds too. Ultrasonic grasshoppers. Yeah, Pia, good. Yeah, some insects hear what we can't. Oh, no, that's the wrong list. Sorry. I wrote grasshoppers in the wrong spot. They hear high sounds, not low. So ultrasonic, yes, grasshoppers hear them. But some other creatures too. Yes, Luca, right. Dolphins. I'm going to talk to you about dolphins too. There's something very cool about dolphins. And our next worksheet is going to be on these creatures. Someone said it, but I need to know. Oh, there it is back there. Christina said it. Bats hear ultrasonic, so bats. Very good. Okay, so the bats I'm not going to tell you much about because you're going to do a little worksheet on that. I'm going to give you 2 weeks for it in case you got questions next week. But dolphins are pretty cool, okay? Dolphins, like bats, send out ultrasonic waves because what are dolphins trying to locate? They send these waves out, and they're trying to locate what? I'm a dolphin. I'm hungry. What am I trying to locate? Food, more specifically. Objects, more specifically. Yeah, echolocation. Each other? Yeah, maybe. What kind of food? Come on, I'm a dolphin. I'm hungry. Get with the program here. What kind of prey? Come on, you ever spend any time in the water? What do you find in the water? Rhymes with wish. Fish. Okay, Molly's got there. Okay, so here's something interesting. So they send out the sound, it hits the fish, and then the sound echoes off the fish, comes back, and the dolphin has a clear idea of how big the fish is, how far away it is, and exactly where it is. Here's something even more fun, okay? I'm a dolphin, right? I send out some waves and I see a whole lot of fish, enough for my whole clan. What I can do is I can go to my clan and I can do this. Ready? I send out waves that are, in a sense, the picture of this scene where the fish are, including where the rocks are and everything else. And the family members can take that ultrasonic picture and know exactly where to go for the fish. Isn't that cool? So not only can they send it out, but they can create ultrasonic sound and make an audio picture for their relatives to tell them where to go and get fish. Yeah, good. Elephants, they can make stopping sounds or noises within their bodies, and it travels through the ground several kilometers to other elephants that are a long ways away. Whales, even more astounding. If you're a whale, you can make certain low sounds, right? Infrasonic, low frequency sounds. You and I can't hear them. They can be heard a long ways away, hundreds of kilometers. They've had whales sing songs, right, off the coast of Europe, let's say off the coast of, I don't know, Ireland, Spain, wherever. And the same song was sung soon after that from whales off the Atlantic coast. So a couple of 1,000 kilometers away. Now, isn't that cool? So whales, their infrasonic sound travels very, very well. And by the way, maybe this won't surprise you, but ultrasonic sound doesn't carry very far. Infrasonic sound carries much further. The wavelengths are longer, and it's easier for that not to get screwed up. Here in ultrasonic, the wavelengths are really short, and it's easy for that to be broken up into pieces. It doesn't carry as far. By the way, I've got 2 or 3 others that have joined me. Anybody else here? Please say hello so I know who joined us. Okay, good. Let's talk about, what did I want to mention? Oh, sound velocity. Lena's here. Thank you, Lena. Good. So remember this famous equation, right? I know it's right on the shiny part. Velocity equals the wavelength times the frequency. Okay, frequency we've talked about, right? Let's talk about the velocity. So velocity of sound in air is about 340 meters per second. Let's take some guesses. Oh, Leia's here as well. Good. Thank you, Leia. Let's take some guesses, okay? What about the velocity of sound in water? Let's say you're a whale. Are you going to experience a higher or lower velocity of sound if you send out some sound in the water? So let's get some guesses from you. So faster or slower, or what kind of number compared to 340? In water, will sound travel faster or slower? What do you think? Got one guess? You got a 50-50 shot. Put in some guesses. Come on. There's a couple others. Good. From Tilly, from Pia. I got a mix of guesses now. Yeah, Christina's giving me a real number. Good. Most you're right. It's faster. Let's think about why. Okay. In air, the particles are pretty far apart. So the waves, you got this air molecules that have to hit the next particle to carry the compression. Remember compressions and rarefactions? Okay, that's the sound particle. So in a sense, if I got water, I got something much more dense. And it's really easy to carry that. If I got cement or brick or steel, there's some steel right there. If I do that, it's way more than 1,000. Whoops. Way more than 1,000 meters per second. So it's really quick through a solid. Okay? All right. What else did I want to tell you about sound? Okay, so it's that way through water or through air, quicker in water. Right, that gets back to the bat sheet, so you'll be able to do the bat problems in your bat cave. Anything else you need for that? That's really about it. Good. Yeah, exactly. Right. In meters per second. True. Good. Yeah, let me think of what else I want to tell you about. Seems like I skipped something on my other board. I did. I got something to show you. Should I show it to you now? Yeah, I will. All right, you might have a pair of these as well. Well, I call it a pair. We just would call it one in German. Now I'm going to undo it here. And I'm going to put them on. And I want you to tell me what these things do for me once I put them. And tell me what they're used for, okay? Yeah, I know, I'm just screwing with you. Yes, it has to do with physics class. So some of you may have a pair of these. These are BOSE is the company, right? They make the best ones. What are these things? Where might I use them? Felix has got it. He says they're sound canceling. Good. We're going to talk about what that does in just a moment. They block the sound, says Kira. Noise cancellation, says Henry. You guys are all on your game. Good. So here's a sound wave. I'm going to race a little bit here. Here's essentially a sound wave, right? I've got compressions. Remember how this worked? Here, this is a sound wave. Sound wave. I've got compressions, and then I got rarefactions where the molecules are farther apart. And then I got maybe another compression over here. Okay, so don't forget those terms. You'll need them for next year. Compression and the spots between the compressions, rarefactions. Let's see if I got a question or two before I go on. Sound is being blocked. Wave interference, good. Would you use them in a plane? Yes, thank you, Henry. That's exactly where I use them, is in a plane. Turns out these are noise canceling headphones. They're really good ones. And let's see how they work out. There's a microchip in these puppies, and let's figure out what the microchip does, or maybe you could guess. All right, so I'll write here. How do noise canceling headphones work? Let me tilt that so you can see it a bit. No, I guess you can see it, all right. How do noise canceling headphones work? Okay, once again, here's my wave. I'm going to do it in black so it shows up the best here. So let's say I got this. I got this. I got this. And I got this. And in between, I got some rarefactions. Okay, let's say that's the plain noise. Okay, so Christina says they play white noise in your ear and they adjust to your surroundings. Yes. I don't know about the white noise, but they adjust to your surroundings. What do? They listen. This is the plain noise, okay? I'll say this in example. Let's say it's not your little brother or sister. You're trying to block the plain noise. So there's the plain noise. What does the headphone do to adjust to this? The headphones make noise that vibrate in the other direction. Well said, Carla. So, in other words, if the plane is this, the microchip that's inside these things sends out another signal. To completely block the sound. So let's see how that would work. So plus, right, like something in math class, this is from the headphones. So they send this. Everywhere there's a rarefaction up here, they hit it with a compression. Everywhere there's a compression, they hit it with a rarefaction. So that if you add them, now I know they don't work perfectly, but if they add them, it's like they sample they kind of what's coming at me? Okay, I hear that plane's motor frequency, so I'm going to send out the opposite. And when you add them, you just sort of get what? Can you guess what happens? Yes, Felix is right. They play the same frequency as a plane does, just offset, right? A half a wavelength offset. Yeah, they're good, Christian. They send out the negative or opposite version of that sound. So if you add it, what do you get? You get just plain old everyday air. And yes, Leah, exactly. They cancel each other out entirely. So I just get something in between, which is a mix of compression and rarefaction. And to you and I, it sounds like silence. So I get a complete destructional interference. How do we call it? Complete negative. I can't remember which name I gave you. Or destructive. Did I give you that name instead? I don't remember this year. It's called negative or destructive interference. Yeah. So sometimes I get something with interference that's what I want. I want to destroy the other sound so I can enjoy the silence and I can sleep better on the plane, right? Now, what they don't destroy is sound of somebody talking on the plane. So if the person's coming up and asks you if you want a Coke or a Diet Coke, you're going to hear that because the microchip does not take out sound that's not just a constant sound. It's the constant sound that these will take out for you, okay? That they will help to block. So, yeah. Good. Let's see if there's any other questions or comments you have about this. Most of you figured that out, which is pretty good. I'll try and get out of the way so you can see. Let me erase a little bit while you're maybe writing something down from the board. Can you see that okay? Oh, that happened to all your teachers? Probably. Are they all in a basement like me? How are we doing on time? We got a few more minutes. Okay, good. I think we're good. Yeah. So you end up with no sound at all. For the assignment coming up, oh, I got a question from Kira. Could you send us a picture of the boards on Classroom again? Oops, Yain. I can't send a picture of that one. I could send a picture of this one, Kira. How about that? The other one I just erased. Sorry about that. I'll try and send a picture of that one, though. Okay. Ute. In the BAT assignment, which is coming up, you get this term, MS. That means millisecond. What's milli mean? Can somebody tell me? So when you get that on the assignment, you know what the heck that unit really is? I'll answer your question, Leah, in just a sec. Millisecond. What's milli mean, somebody? Milli. You'll need that. Good. Several of you got it. Not thousand, thousandth. That's right, Kira. Thousands, not quite. No, thousand would be kilo. 1,000 is a kilo. Careful. Right? Kira has it as 1,000th. So it's 1,000th. Or in other words, 1 millisecond is 0.001 second. Okay? So when you're doing the assignment, you need to know that. Google it if you forget it. Okay. Good. Let me look at my list because I feel like I forgot something. Oh, I was going to answer a question from Leah. How will the science hours work next week? Leah, I don't know. Do I teach you guys next week? I know I have like a ninth grade coming up, but I don't know if I teach you folks. I hope I do. If I do, we're just going to pick off right here and I'm going to bring some demonstrations to class to show you. If I don't have you, then I don't know what they're teaching you and I don't know who is teaching you. So that may not be much of an answer, Leah, but that's as good as I can get right now. You guys got an email? You only have bio next week. Not that I don't like bio, right? But I mean, physics, golly. Angel is going to be the teacher. Angel. I don't know who Angel is. Okay. All right. Okay. Thanks for sharing that with Leah and with me too. I miss you guys, by the way, and I hope you're getting on all right. It's not easy. At least as 10th graders, you get some hours. The 7th, 8th, and 9th graders have nothing. So that's pretty rough. Yeah. At any rate, we're hoping in the fall things will be more normal. Also, I want to say you guys have done good in physics. I hope some of you picked Lystom's physics or are going to be thinking of taking AP physics at some point because I got a lot of talent in this class. Sometimes you're pretty noisy, but there's a lot of good brains out there. So think about taking more physics and more chemistry. I teach chemistry too. I love chemistry. Okay, let's get back to physics a little bit. I'm going to look on my little cheat sheet and see what I forgot to tell you. Okay, we did infrasonic, we did ultrasonic. Oh yeah, okay, sorry. Uses of ultrasonic sound. You've had this in your life, ultrasonic sound. Does anyone know where it's used? You might even have something like this in your home. Ultrasonic sound. Super. Good one. An important one, Carla. So seeing babies in the womb. So it's called in German an Ultraschall. Ultraschall. In English, it's called an ultrasound. So I'll say ultrasound to see unborn babies. What else, though? What else? Not just unborn babies. Oh, Helen is here. Helen Stahl is here. You're kind of quiet, Helen. I didn't know you're here. Well, it turns out, okay, you got some other stuff too. Yep. Okay. You can use it on different parts of your body. Like if you have a knee problem, odds are good the doctor, he or she is going to come along and do an ultrasound and look at with ultrasonic sound and see a picture of your knee or your ankle or your elbow or whatever you've screwed up. So it's not just for looking at unborn babies, but any sort of part of the human body that is not just bone, where they need to see flesh or ligaments, okay? So I'll say, or parts of you. Right? They send the ultrasonic sound into you and it bounces back. And by the way, it bounces because it goes different speeds at different materials, flesh, bone, sinew, okay? It gets a three-dimensional picture and they can see what's wrong with your joint or whatever it happens to be. Right, for injuries, exactly, Kira, right. Christian mentions sonar. Yes, although that's not, I don't know if that's ultrasonic sound for sonar. I thought it was actually infrasonic, although you can check on that, Christian, and tell me what frequencies they use. The other thing they do is Ultrasound is used to eliminate or lower pollution levels. And the fancy name for pollution levels, it's called emissions. And coal burning power plants, which unfortunately is still most of the way the world gets their electricity. So here's some dirty coal particles. If you shoot them with ultrasonic sound, they clump together and fall down to the bottom where they can be collected and taken away before they get into the air. So ultrasonic sound can cause clumping, and then it falls down, and elimination of emissions. Emissions are like bits of nasty unburned coal or solid carbon or impurities in the coal that you don't want to breathe. So it's a good thing to have happen. Good. Our time is up, and I'll take a picture of the boards as they are and put that up on there. Unless you haven't told me that you're here, then I'm going to wish all the rest of you a good day and good teaching or learning next week. And yeah, write me with your questions and maybe some answers as well. Thank you for participating. See you next week. I'll send you a time in the Google Classroom. Bye-bye.